Hello everyone, and welcome back to Thermodynamics. So we've been talking about how to apply the first law of thermodynamics, which is conservation of energy, to closed systems. Remembering that closed systems are systems where we can't transfer mass between the system, which is shown here in gray, and the surroundings, shown in blue. Now, I've been saying whenever we face a problem like this, there are really three questions that we want to ask ourselves. The first is, what's inside of our system? Is it air? Is it water? Is it some other type of material? The second is we need to ask ourselves whether the system is open or closed. So far, we only know how to use closed systems, and because we have a closed system, we're going to use the closed system version of the first law, which is down here. Then the third question we have to ask is, what happens to the system? So as I move between my two state points here at time 0 and time tau, how is energy transferred? What percentage or how much of the energy transfer is due to heat and how much is due to work? So we've come to this kind of pivotal point in thermodynamics where we're going to start really using the first law. So we have this first law equation, which tells us that the change in total energy of our system, delta E, is equal to the amount of heat minus the amount of work. Now we know how to find work because it's the integral of P dV. But what we don't really know how to do is find Q or find delta U. Now remember, delta E only becomes delta U if the change in kinetic and potential energies, or energy stored inside of a spring, are negligible, meaning very small, compared to the change in internal energy. Now, this is true for a lot of the heat engines that we'll be talking about in this class, talking about things how your car moves, so how do car engines work, how do jet engines work, how do we produce power from nuclear power plants or coal-fired power plants or natural gas power plants. And in most of these systems, those other types of energies are not large compared to changes in internal energy. Now, for closed systems, we have a couple of special cases. Now, we call these simple systems, and it's important to remember that simple does not mean easy. It means less complicated. So in these simple systems, they're less complicated because they only have heat transfer or they only have work. So in our picture, we have two different types of simple systems here. The first simple system A, only transfers heat between the system and the surroundings. So we know that the work term here is equal to 0. So all the energy change in our system is because of heat transfer. Our second type of simple system is the opposite of that, where we have all of our energy transfer coming as work that's transferred between the system and the surroundings, and there is no heat transfer, or the heat transfer is negligible. So if we have simple system B, delta U is equal to negative W from 1 to 2. We get that from the first law. And we find work as the integral of P dV. So here we could find delta U if we knew the work. In the simple system where there's only heat transfer, if we could measure the amount of heat that's transferred between our system and the surroundings, we could use that to get delta U. Unfortunately, you won't really learn how to calculate heat transfer until you take heat transfer, right, which happens in third year. But in both of these cases, we could find delta U if we knew how. And the focus of this lecture today is going to start to introduce to us how we find delta U. So conservation of energy for closed systems, after we make some assumptions about kinetic and potential energies, becomes this equation. The change in U, which is U2 minus U1, is equal to heat minus work. We know that work is the integral of P dV. Now, in a normal case, at least for what we know right now, we can't find delta U and we can't find Q. I'm going to make the argument to you that most times in closed systems, you'll use the first law to find the heat transfer. And that means we need a way to find delta U. Now, it's a little tough to find the actual change in internal energy in any system because it depends on how much stuff you have in a system. So I can't have, I guess a little bit like the Matrix, right? Like, where you can get anything you want and have just an infinite selection of anything at your fingertips. And I guess maybe we have that on the internet, but this becomes a little bit easier if we think not in terms of the change in internal energy, but the change in specific internal energy. Now remember that specific internal energy is an intensive property, and it does not depend on mass. So to get specific internal energy, we took the internal energy, that's capital U, and we divided by the mass, and that capital U divided by mass is equal to lowercase u, or specific internal energy. And the nice thing about this is that the specific internal energy for any type of mass that's at the same state is going to be the same, no matter how much of that mass you have. And then you make the answer unique to your problem just by multiplying by the amount of mass that you have in your system. So if we could find those specific internal energies at state 2 and state 1, and we knew P as a function of volume inside of our system, then we could find work. And the only unknown we would have in the first law is heat transfer. And that's what we're going to try to do for most closed system type problems in this course. So today we're going to think about how we find specific internal energy. So how do we measure internal energy? Internal energy is the energy that's associated with the motion of molecules in a substance, and it's difficult to measure directly. So we don't really measure this directly, at least usually, not in this class, right? So here, we don't have to measure this directly, because instead, we're going to use the fact that when you fix a state, you know everything about the substance that's at that state. So if I could fix the state, then I would know everything. And since the internal energy is something about my mass at that state, then I would know the internal energy and the specific internal energy. So we have a lot of tables. So I don't know if you have the textbook yet, but if you do, you can look in the back and maybe, 15% of the textbook is just tables at the back. We're going to use these tables a lot, right? So here's kind of a photocopy of one of those tables. And this says property of superheated water vapor. So that's steam, right? So steam that's above the boiling temperature. Now, if I knew that my water in my system was superheated, and I knew the pressure, right? So this table is for water that's always at 80 bar or 8 megapascals. And I knew the temperature, then I could find the specific internal energy. I know this, it's a bit of an eye chart over here, but this column here is specific internal energy. So that's what's highlighted here. And then I could just read that off the table if I knew the pressure and the temperature, because pressure and temperature are both intensive properties. And as long as I'm not in the process of boiling water, pressure and temperature are independent. So that means that if I know one, I don't automatically know the other. So if I have two independent intensive properties, remember those are properties that don't depend on mass, then I'll be able to find anything about my system, including the specific internal energy. So we're going to start to learn how to use these tables in this lecture. So we want to find the state of the mass that's inside of our system at a given time, let's say, in these closed systems. So here, there's a state of a closed system at thermodynamic equilibrium, so that means that things aren't changing, is described only by its thermodynamic properties. So when you know the state of a substance, then you know all of the properties of that same substance. So if I know two independent intensive properties, then really I know, or at least I could look up all of the properties of that substance. So how do we find states? We've talked a little bit about drawing these PV diagrams, right, to look at processes. Now the points, my processes are the arrows, right? So the points here are all state points. So as I look at this first process, as I go up here, right? So this is my pressure is decreasing and my volume is increasing. So maybe this is a piston cylinder assembly where the piston is receding. So the volume inside the cylinder is getting bigger, right? The volume is getting bigger, the pressure is getting smaller. So if I can draw this, then maybe I know something about the state, right? And we've said that to fix the state, we need two independent intensive properties, right? So if I was on this graph and pressure and volume were independent, then if I knew those two things, I could find a point on the graph. And anytime I can find a point, that represents a state. We have to remember, again, that intensive properties do not depend on the mass. So if you have an extensive property, something like internal energy, what we would typically do is divide it by the mass, and then we would get the intensive version of that property, and we'd put the word specific in front of it. So then we'd have specific internal energy. Now this is pressure versus volume, and volume is also an extensive property. So on tables, when we're looking things up, we'll talk about specific volume, which is the volume divided by the mass. It's also the inverse of density. So now we have to think, are two properties dependent or independent, right? So if it's independent, that means that if I know one of these properties, I don't necessarily know the other. So we just talked about density and specific volume. So if I know the specific volume, I automatically know the density because it's just the reciprocal, right? So those are two dependent properties. So you can't know density and specific volume and expect to be able to fix a state. So dependent properties include things like density and specific volume, which we just talked about. Now, independent properties, pressure and specific volume are independent. Temperature and pressure are sometimes dependent and sometimes independent. So we have to know something about the mass that's inside of our system. Basically, if we're thinking about water, if we have liquid water, temperature and pressure are independent. If we have pure steam, then temperature and pressure are independent. But if I tell you that you have a pot and you're boiling water at atmospheric pressure, you already know what the temperature of that water is. So temperature and pressure are dependent when phase change is happening, right? So I don't know what, I grew up in Canada, so I don't know what water boils at in Fahrenheit, but in Celsius, which is sensible sort of units, if you're talking about atmospheric pressure here on Earth, then the temperature that water boils at is typically 100 degrees Celsius. So we talked about pressure versus volume curves, but really you can plot the state of any material on this three-dimensional graph where you have pressure, specific volume, and temperature, right? So you have this space, this three-dimensional space where you can find any state. So this is a PVT surface. So here there are some single-phase regions. So we'll think about water. So there's some regions in this three-dimensional space where the water is liquid, that's a single phase, or it's vapor, also a single phase, or it's ice, which is a single phase, right? So it's a solid. But then there's some two-phase regions here, and the two-phase region that we're mostly interested in. Remember, early in the class, I talked about how when mechanical engineers have heat, a lot of times we want to boil water because that makes the water molecules expand and we can force that steam through a turbine and generate power. So because we're often talking about power generation, we'll often be interested in fluid that's boiling or condensing. So two-phase regions are important to us, particularly as we're moving between liquid and vapor phases. So if there's only one phase present, we can have either solids or liquids or vapors, right? Or gases, right? And then the two-phase region, at least the two-phase region that we're most interested in this class, is this liquid vapor region, right? So we call this a vapor dome because it looks a little bit like a dome, right? So this is the vapor dome where we have some liquid and some vapor. And anytime you're in this process of phase change, so again, if you're at atmospheric pressure and you're boiling water, so that means you have some combination of vapor or steam and liquid, then you know that all of that combination is going to be at the same temperature, which is the boiling temperature. We call it the saturation temperature, and that's so everything is going to exist at that temperature. So there, pressure and temperature are dependent if you know that the phase change is happening. So here, under the vapor dome, pressure and temperature are dependent. So if we're under the vapor dome, we might need a new kind of property to describe what's going on in our system. So here, we'll call this new property quality. So quality is the mass fraction of vapor that's in this steam liquid water mixture. Quality is defined here as X, and that's going to be the mass of vapor in our mixture divided by the total mass. So quality has to go between 0, which means that there's no vapor, and 1, which means that it's all vapor. So here, if we follow this line here, and hopefully you can see that on my pointer, we would have quality of 0 on the left-hand side of this vapor dome and a quality of 1 here on the right-hand side of the vapor dome. So that's how quality moves in our system. I know it has to be between 0 and 1. So when we get to the interface on this graph between sort of the single phase regions and the multi-phase regions, then we call those saturated states. So if I'm on my blue line that I'm showing here, I would have saturated liquid. So let's say you're going to try to make some macaroni and cheese. You put your pot on the stove, and now it's heating up. It starts at maybe 4 degrees because you got it out of your tap, and it heats up and it heats up. Now, eventually, it's going to get to 100 degrees, right? Assuming you're at atmospheric pressure, the water would start to boil at 100 degrees, but you can be at a state where all of the water is at 100 degrees. And if you put in just a little bit more heat, you'll start to break apart those water molecules so that they're further spaced, and you have some amount of steam or water vapor and some amount of liquid. But as you're just getting to that point, you'll have all the water as a liquid at this saturation temperature. So your quality will be 0. Now, if you keep adding heat, so let's say you have a sealed container. You keep adding heat, and what happens is the temperature stays the same as these water molecules start to sort of break apart and move from a liquid into a vapor. But if the vapor phase got any hotter than the saturation temperature, what would happen is it would start to transfer heat back into the liquid water. The liquid water would absorb that heat, but that extra energy would cause the water molecules to move further apart, making more steam. So then what happens is, as you're changing phase, as long as there's a little bit of water left, the whole temperature of the mixture will be at 100 degrees. But eventually you'll get to the place where you've evaporated or boiled off the very last bit of liquid water, and you're all at vapor. So now, again, you're still at atmospheric pressure. So your whole temperature of that mixture, even though we just got rid of the very last bit of water, the whole temperature of the mixture is still at 100 degrees, but you have all steam. So that's saturated vapor. So that's your quality is equal to 1. Now, the problem with vapor is, so water is a great heat sink. It takes a lot, maybe you've noticed this, right? A watched pot never boils. So it takes a lot of energy to increase the temperature of liquid water. But once you get to this point where there's no more liquid water there, it doesn't take very much energy to increase the temperature of steam or of water vapor. So the temperature will run away on you very quickly. So you probably don't want to get to this point where you've evaporated all your water if you're making macaroni and cheese, right? Which makes sense because now you've got nothing to put the macaroni in. So if we look at the vapor dome, right, it looks almost a little bit like a mountain. And there's a peak at the top of the mountain, right? And this is called the critical point, right? So the critical point is the intersection of saturated liquid and saturated vapor lines, right? So this is the very top of our vapor dome. And this point is called the critical temperature. So this is the maximum temperature when liquid and vapor can coexist at equilibrium. So this means that you could design a system, as long as you're below this critical temperature, where you could have both saturated water and saturated vapor, and they could exist at steady state. So you could keep them there. But if you're above this critical temperature, then what happens is you'll sort of flash boil. You'll go right from liquid and you'll flash into vapor at equilibrium. So you can't have this combination of water and water vapor if you're above this critical point. There's a pressure that's associated with this with this top of this curve as well, and that pressure is called the critical pressure. So you may have seen, so it's tough to draw three-dimensional surfaces. Maybe, well, at least for me, I don't know, maybe you're better at drawing than I am, but often we don't draw this whole PVT space. Instead, we'll take some projection, some slice of this, right? So this is a pressure versus temperature curve. We already talked about pressure versus specific volume or pressure versus volume curves, right? So a lot of times we'll sort of have a two-dimensional representation of these kinds of graphs, right? And here the lines indicate where you're changing phase. But it's only a line on this graph if we take a PT graph. And we like being able to see the vapor dome because so much of what we're doing happens when we're changing phase. So we really want to know what's going on when we change phase. So in thermodynamics, we typically don't talk about these PT planes. If we did, then we would say, okay, now I know this temperature, right? So if I know the saturation temperature, I can go up to this line and then see, oh, where does the phase change happen? And that tells me the saturation pressure. Again, because we live on Earth and the pressure here is usually, at least if you're at about sea level, about 101.3 kilopascals, we know, we're very familiar that the saturation temperature of water at 1 atmosphere is 100 degrees Celsius, because at that pressure, that's where water boils. But if you live up in, say, a mountainous region like Colorado, then what I've heard is that it's hard to boil beans in Colorado if you're up on a mountain, because the water actually boils at a lower temperature than 100 degrees. So then it's hard to cook something like beans. So then what you do is you use a pressure cooker. So you seal in your system, and then as you start to boil that water, which is boiling at a temperature lower than 100 degrees, you're increasing the pressure in the system. And as you increase the pressure, then that's kind of like, if you think about the pressure, it's forcing those liquid molecules closer and closer together, which means that it's harder for those liquid molecules to separate into vapor. So then as we increase the pressure, we also increase the saturation temperature, which you see on this graph as well. So within two-phase regions, pressure and temperature are not independent. So we've talked about that. If you tell me the pressure, then I can tell you the temperature at which water boils. So those two things are dependent. So why do we care about this for thermodynamics? A lot of what we're interested in is how do we boil water to get steam and then use that steam to get mechanical energy. So phase changes in this class are really important. In particular, the phase change as we move from water to water vapor or steam. So we will often look at a PV diagram, which is shown here, right? So here, now we have pressure on the vertical axis and volume on the horizontal axis. So this is, again, a two-dimensional slice through that three-dimensional PVT curve. When we draw temperature versus specific volume, the vapor dome starts to look like this for water, right? So basically, anytime I'm on the left-hand side of my vapor dome, I have liquid. Anytime I'm on the right-hand side, I have vapor. And anytime I'm so I'm underneath the vapor dome, then I have some combination of liquid and vapor. So what's interesting here too is we have some constant pressure lines, right? Because we know that we're interested in P and V and T and V, right? So I have constant temperature lines are any horizontal line on this graph. Constant specific volume lines are any vertical lines. But here, if I have any constant pressure lines, this constant pressure line moves up from, this looks like 1 to F, maybe it's L, from L to F to G to S. So these funny looking lines that are going up and to the right, but are flat under the vapor dome, those are constant pressure lines. If we want to find a state, right, if we want to fix a state, we basically need to find a point on one of these graphs. So we need to know two independent intensive properties, because if I know those two things, then I can define a point. And actually here you can see why knowing a pressure and a temperature is dependent under the vapor dome, because if I know a pressure and a temperature, because here my constant pressure line is also a horizontal line. So if I only knew pressure and temperature, and I knew my fluid was boiling, I wouldn't know how much saturated liquid I had and how much saturated volume I had. But if I was here in the liquid region, then I have this line that slopes up. So if I knew specific volume and I knew temperature, I could find where those two lines intersect. Or over here in the superheated vapor region, I have a line again that is not horizontal. So if I knew the specific volume of the vapor I was talking about and I knew the temperature, I could find where those two lines intersect. So really, when I'm talking about trying to find two independent intensive properties, I'm really trying to put a point down on this TV diagram, or a PV diagram here on the right. So these are all just vapor domes. So how do I know what table to look in, right? Because there's all kinds of different tables in your textbook. So what I always like to do is I like to ask first, what's the fluid? We'll often be talking about fluids in this class, whether that's air or liquid water or vapor or some combination of the two. So we need to know, basically, is it air or is it water? So that'll divide us into which table to look at. But then if it's water, I need to know, is it liquid water or is it water vapor or is it some combination of the two? And that's how I'm going to figure out which table to look in. So here's another graph of a TV diagram, right? And this is a vapor dome. So here I have liquid water as long as I'm above the blue line and to the left of the vapor dome. It's subcooled because we know that it's below the temperature that we need to boil at. Or it's a compressed liquid because we know we increased the pressure. We sort of forced those molecules back together into a liquid. And if I'm looking on a table to try to find these things, I'll look at table A5 in your textbook. Here's the saturated liquid line. So this is the dark blue line here. So the blue line on the vapor dome. So this is, we have all liquid, but the liquid is at the saturation temperature or the boiling temperature for the given pressure. So here, temperature and pressure are no longer independent. This is the line. If you're heating your water up inside a pot to make your mac and cheese, then this is the point where temperature and pressure are no longer independent. If we're above the vapor dome and to the right of the critical point, we have superheated vapor. So this is vapor that's above the temperature that it needs to boil for the given pressure. If we're trying to find these superheated vapor data, then we look at table A4 in our textbook. The red line is the line for saturated vapor. So this is when we're right on the cusp of the vapor dome. Here we could look in the superheated vapor data, but we can also look at the two-phase data that we'll talk about next. So when we're under the vapor dome, we have this two-phase mixture. We know that we're at the saturation temperature and we're at the saturation pressure, but depending where we are on a horizontal line, we'll have either more saturated liquid, or as we move to the right, more saturated vapor. So our quality is going from 0 at saturated liquid up to 1 at saturated vapor. So here we're going to use either table A2 or A3. I believe table A2 is when you know the temperature, and table A3 is when you know the pressure. Like we said, under the vapor dome, P and T are dependent. So we need another independent intensive property. And oftentimes we'll talk about quality. Remember, quality is the mass fraction of vapor inside your two-phase mixture. So it's what percentage by mass of your mixture is vapor. And it moves from a quality of equal to 0 at the blue line to a quality equal 1 at the red line. So here's kind of a thought example. We're going to start at state, again, I'm not sure if this is 1 or state L, right? L probably because it's liquid. Let's go with L. So again, we're going to start at L. right? So imagine your pot that you're boiling water in looks like this because it has a piston on top, and you've got a system that's full of liquid water, but this can expand as we start to boil and our specific volume changes. So we start adding heat. Now we add heat. We start off with liquid water that came out of the tap. Well, here it says it's 20 degrees. So it came out of the tap. We sat it at room temperature for a while, and now we're going to start to boil it, right? And what happens is this temperature increases, but it stays at liquid water. So it doesn't really look that different, but if you stuck your finger in it, you would definitely know the difference between 20 degrees and 100 degrees. Eventually, we'll get to the saturation point. So if this pressure is set up to be atmospheric pressure, then the saturation point will be at 100 degrees. So now we'll start to boil. So we'll, as we're boiling, we'll have some combination of liquid and water. Now, even though we keep adding heat, the temperature, because the pressure stays constant, the temperature in our mixture is also going to stay constant. But over time, as we add heat, we'll get less water and more water vapor. So our quality will move from 0 towards 1. Eventually, we'll keep adding heat, we'll keep losing liquid water, and we'll get to a point where we have all water vapor. And all that water vapor will still be, for some amount of time, all that water vapor will still be at the saturation temperature, right? So if the pressure here is 1 atmosphere, the temperature will still be 100 degrees. But then as we add heat, the only thing the water vapor can do to accept that energy is increase in temperature. So there's no more water to boil. There's no more kind of sacrificial water in here. So as we add more and more heat, we keep ramping up the temperature of that water vapor. So just to review, if we're trying to look things up on tables and we have only liquid, then we look in A5. If we have only water vapor or steam, then we have A4. So let's run through a bit of an example. Here, we want properties associated with superheated water vapor. So it tells us that it's water vapor, which means that we need to be in table A4. Now it tells us the pressure and the temperature. And because we're superheated water vapor, temperature and pressure are independent. So first, I always want to look for the pressure if I'm using table A4. Table A4 is really a collection of different tables for different pressures. So first, I find the table that's at the right pressure. So 10 megapascals is 100 bar. And it also tells me here the saturation temperature. If I was at 100 bar, then water boils at 311.06 degrees Celsius. So much higher than at atmospheric pressure because that pressure is forcing those molecules closer together. But now I know I'm also at 400 degrees. So I found the right table for my pressure. And then I find the row on that table that's associated with my temperature. So now if I was looking for the specific internal energy, little u, then I would just read that number from this column. If I wanted the specific volume, which is 1 over the density, I can read that off from here as well. We'll learn about H and S as we move through the class. Right? So I can write down here for all the properties, right? Because what we said is anytime you know 2 independent intensive properties, you know all the properties. You just have to look them up. So this is great if I'm right on a line, right? But here, if I look at this table, it doesn't give me rows on the table for every different temperature, right? So 400 makes sense, and 440 makes sense, and 480 makes sense. But what if I was 416 degrees? So the problem is all of these properties vary non-linearly with temperature. But if you take a class that talks about nonlinear processes, sort of the first thing that they'll do is kind of ask you to get data points that are close together and assume that even though it's nonlinear, the nonlinearity is small in whatever range that you're talking about. So that's exactly what we're going to do when we look at these tables. We're going to do what we call linear interpolation. So I'm going to assume, in this case, that I have a value of specific internal energy for my low temperature and a value of specific internal energy for my high temperature. The temperature I'm interested in is actually somewhere in between Tmin and Tmax. So what I do is I define my temperature range, delta T, and my specific internal energy range, delta U. And I'm going to say that these properties vary linearly in between the 2 points that I know. So if I'm looking for some temperature in my range, I would draw, graphically, I would draw a line up from this temperature that I want until I hit this linear line with the slope that's given by my points. And then I draw a horizontal line over, and then I would find the specific internal energy that's associated with that temperature, or at least an estimate of that value. So the way that I do this, and there's lots of different ways to do linear interpolation, but I always think about the percentage difference that I've gone in the range. So if I've gone some percentage A, or actually it's a per unit value, I guess, because it goes between 0 and 1. So I've gone some per unit value in my temperature range, A. And if I've gone that same value, so let's say it's 25%. In this graph, it looks like it's maybe 25%. So if I've gone 25% of the range in the temperature range that I have, that means I also have to have gone 25% of the range in the specific internal energy range that I want. So here I define this per unit value A as T, that's the temperature that I'm interested in, minus T min, that's the temperature on my table that's just below the value that I'm looking for. And then I'm dividing by T max minus T min. So T max is the temperature that's above the temperature that I'm looking for on the table. And T min is, again, the temperature just below it. So if I do this, I'll get some value of A between 0 and 1. And that's kind of the per unit change on my temperature range. Let's say it's 25%. So if I've gone 25% of the range of my temperature, that means I've also must have gone 25% of the range for my specific internal energy, if I assume that this is linear. So here, in this graph, I would use, or in this equation, I would use the known value of T to find A. And then in this equation, I would know A because I found that previously, and I'd rearrange this to find the specific internal energy that I'm looking for. Now, conceptually, that's how we do linear interpolation. So I know we've sort of been introduced to a couple different concepts in this lecture, so we're going to leave it here for now. But then when we pick up next class, we'll go through several different examples of how to do linear interpolation to fixed states. And we'll look at subcooled liquids, superheated vapors, and two-phase mixtures. Thanks again for joining me on thermodynamics. I'll see you next class.